Welcome everyone. This will be the first in a series of lectures. This is Algebra 3, Chapter 3, Section 1. This video is for March the 23rd. We're going to go through several examples today in this section. There will be assigned problems associated with the section. They're up on the board. The first assignment will be due this evening by 9 o'clock. It's numbers 5 through 30 from page 250. And there will be a secondary assignment due tomorrow from the same section, numbers 31 through 48. I've created a discussion assignment on my school app on our page so that as you're working through problems, if you have questions, please enter your questions into the discussion assignment. And I will be answering the questions throughout. I'll be monitoring that assignment. Also, I've opened up an assignment to receive your homework. Normally we don't turn homework in, but for the duration of the distance learning process, what we are requiring, what's being mandated per the school, is that you create a PDF of your work and that you'll upload it, you will submit it digitally for me to review. If I find that you are not completing and uploading your assignments when they are due, then I'll be reaching out and discussing with you what's going on. So there's an expectation that you're watching videos, which is how we're going to learn the material, and that you are continuing to practice your problems and upload them to the digital assignments. Again, please use the discussion assignment if you have any questions along the way. So here we go, 3.1. Quadratic functions. We've done a lot of work with functions up to this point. We've done a lot of work with quadratic functions. Just to be reminded, quadratic implies that the function has a degree of 2. Unlike the quad, that's where I was headed, quad meaning 4, but this time we say that the degree equals 2. We think of f of x equaling x squared. That's what we would have called the parent function. And you know from previous discussions, the domain of the parent is all reals. We would call this a continuous function. We're not picking up our pencil anywhere when we draw it. However, the range of the parent function is from 0 to infinity. The graph is a parabola. It's that U shape, and in the parent form, it's going to open up. And both then the x-intercept and the y-intercept are, in fact, the origin. If you open your textbooks with me, I'm on page 244, and if you are currently at home without your textbook, if you look on the discussion assignment, in the My School app page, you will notice I have put in there PDFs for the first few sections of Chapter 3. So by all means, feel free to open up those attachments and you can go ahead and find the proper sections. So draw your attention then to page 244 and 245. You'll notice that they have revisited the definition of a quadratic function in what we would call the Jumbo form. And we worked a lot with these in Chapter 2 when we were solving quadratic equations. We know that f of x equals ax squared plus bx plus c. A being the lead coefficient, b being then that coefficient of our linear term, and c being the constant. Now, the sign of A is extremely important. If A is greater than 0, our parabola opens up. If A is less than 0, the parabola opens down. If A equals 0, no parabola. We're back to a linear function, like the y equals mx plus b. If you would take a look now on page 245, You'll see a big box with the basic characteristics, and we've been through this before. You will notice, however, a little bit of new terminology when we are talking about a parabola, and I'm going to go in more generic or generalized form as opposed to the parent function. This relative minimum is now known as the vertex. And yes, it's an ordered pair x and y, but for the purposes of our discussion, we're now going to start calling this h and k. H and k, the x value being h, the y value being k. This is the minimum, or if it had been turned upside down, this vertex very well then would have been a relative maximum. And we've used that terminology before. We've done calc min, we've done calc max. We've been able to find those locations where the behavior of the function changes direction. So again, belly of the whale, top of the mountain, you've heard me say that time and time again. Now, despite the fact that my drawings aren't so beautiful, we talked about that many, many times, these parabolas are symmetric. In other words, I could fold my paper about a vertical line, and that vertical line then would create the identical images. In the parent form, it is in fact the y-axis, which acts as the line of symmetry. So in parent form, we say that the y-axis is the line of symmetry. Now, we know this because this f of x equals x squared is an even function, such that f of negative x is equal to f of x. We've looked at that in the previous chapter. However, be reminded that the y-axis has an equation. I ask you this time and time again, what is the equation of the y-axis? Well, the equation of the y-axis is x equals 0. All vertical lines have an equation in the format x equals a number. Well, if we pick the parabola up and we move it about, we use the transformation techniques that we learned in chapter 1. If we pick the parabola up and we move it about, then that vertex moves with it. But what I can assure you is there always still exists a line of symmetry. And that line of symmetry is defined by the equation x equals h. And h again being the x value of the vertex of that parabola. So let's take a look over on page 246. Let's take a look at a couple of examples. On 246, we'll find a series of drawings which are some transformations now. We've got the horizontal transformation, these are the rigids. We've got the vertical displacement up and down. We have, remember, the reflections with respect to x-axis and y-axis. I draw your attention very specifically to the checkpoint for the example number 1. In this checkpoint in particular, we've been asked to sketch by hand. Well, to sketch by hand means to use all the knowledge that we have about the functions and their behavior and to keep the calculator at rest. So if we sketch by hand, g of x equals x squared minus 4. So this again is checkpoint number 1. G of x equals x squared minus 4. Well, again, this is the quadratic function, and we know it because it has a degree of 4. It has a separate term, which indicates we're going down 4 units. Down 4 units. You will notice that the parent function was here. If we drop down 4 units, the new function g of x is here. So g of x squared minus 4. Line of symmetry, still x equals 0 because the vertex is at 0, -4. We have not shifted left and right. We've only shifted up and down. So x squared minus 4. h of x in letter B, that's going to take on a little bit more of an interesting view because we've got a bit more going on in letter B. Letter B says h of x equaling x minus 3 quantity squared plus 1. Here we've got both a horizontal shift and a vertical shift. Now remember, vertical shifts go in the logical direction of the sign. So this is a V shift up 1. However, the horizontal shift, remember the 3 is considered positive and this is a -3 or a subtraction of 3. So here we're going to actually go right 3 units. So again, if I compare the graphs to the parent function, here's the parent function, and I'm now going to move right 3 and down 1. My new vertex is at 3, -1. So this is h of x. So this is the new vertex. And then the new line of symmetry, again, comes from the x value of the vertex. So the line of sim is x equals 3. So to do some, I'll say, simple graphing by hand relies on our knowledge of transformations. Recall, if I were to have put a negative in front, that would have been a reflection with respect to x-axis. If I had put a negative in front of the x, but before the squaring, again, think PEMDAS here, before the squaring, that would have been a reflection with respect to the y-axis. So sketching by hand, think about the movement of the vertex. Feel free to pick a few x values, plot a few points, plug the x values in to make sure that you're moving in the correct direction, and then connect the dots to make a smooth curve. Over now on the top of 247, I draw your attention to the distinction between the formats. We said a moment ago that the general form of the quadratic is f of x equals ax squared plus bx plus c. Again, a, b, and c are all real numbers. But now we're moving into something called the standard form. This is the same parabola, but we're going to express it a little bit differently. This is going to be a times the quantity x minus h squared plus k. Notice again, h and k are the vertex. X equals h will be the line of sim, and the sign of the a value will determine whether we open up or whether the parabola opens down. So for graphing purposes, the standard form of the equation of the parabola is a much more powerful tool for us to be able to use to do some analysis. Notice, in the checkpoint 1b, we really were already set up in that format. So what happens if we are provided with a general form, but we're asked to comment about the behavior of the graph, the nature of the function, anticipate what it's going to look like before we ever put pencil to the page. So I take your attention now over to example number 2. I'm going to actually do this example 2 ways. So I'm going to ask you to really stay close tension-wise here. I'm going to use what we call a vertex form, and then I'm going to do one of our favorite things to do, complete the square. So again, this is the example itself, and I'm going to do a side-by-side comparison of 2 solution methods, using 2 solution methods. first method we're going to use is the vertex method. For the given function f of x equaling 2x squared plus 8x plus 7. Again, this looks like the general form, ax squared plus bx plus c. Right away, I'm going to utilize a couple of quick formulas that says that the x value, which we call h, of the vertex of this parabola comes from the opposite of b over 2a. We've kind of heard some of that before when we were unpacking the quadratic formula. Again, these are not unrelated topics. Once we find the value of h, to get k, the y value of the vertex, it's simply f of h. So here we go. For the given example, a equals 2, b equals 8, and c equals 7. You can pick those off directly. H again is going to be the opposite of b. Well, that would be negative 8 over 2a. Well, a is 2. So this is going to be negative 8 over 4, and h therefore is negative 2. So the x value of the vertex of this parabola is negative 2. Then to go back and find the k value, the y value of the vertex, because again, that's what this is all about. We're going to find f of negative 2. So we're going to take the negative 2 that we just found, plug it in for x. So that's 2 times negative 2 squared plus 8 times negative 2 plus 7. And we're going to simplify that, and that's going to equal negative 1. So therefore, I know that the vertex is going to be at negative 2, negative 1. Now, whether I'm in this standard form or whether I'm in the general form, the a values are the same. A is the same a here as it is in this location. So now if I'm going to put this into standard form, the a is 2. This is x minus, now be careful, the h itself is negative. So this is x minus a negative 2 quantity squared plus k, well k is negative 1. Which means this really equals 2 times x plus 2 quantity squared minus 1. This is the standard form of the equation of this parabola. This is the standard form of the equation of this parabola. I can tell you that its vertex is at negative 2, negative 1. Since a is greater than 0, we know that the parabola opens up. And I can tell you that the line of symmetry, is at x equals negative 2. So if I was going to do a quick sketch, what would this look like? Well, here's the parent function. I've gone to place my vertex now at negative 2, negative 1, which means I've gone left 2 and down 1. A is positive, so I'm opening up, and oh, by the way, I have a bit of a vertical stretch because that multiplier is greater than 1. So this one would be just a bit taller and thinner than the parent function. So this is me using the vertex method to convert from general form to standard form. Now let's do the same problem again, completing the square. Remember, completing the square allows us to create a perfect square trinomial. That's the goal of completing the square. And we're going to rewrite that perfect square trinomial as a binomial squared. Well, if I take a look at this standard form, this x minus h quantity squared, that's a binomial squared. That's a PST. That is embedded, it's a part of this standard form. So we're going to take the same exact function that we had a moment ago, f of x equals 2x squared plus 8x plus 7. Now the lead coefficient is a 1. In the last chapter, we just got to divide everything by that lead coefficient, both sides, and we got rid of it. The distinction here, though, is there is no both sides. There's not a 0 there. There's an f of x. So this time, all the work that we do has to be done on one side. So here's how we're going to do it. We're going to group the first two terms on purpose. We're just literally going to put parentheses around the quadratic and the linear term. Then we're going to factor out that lead coefficient. We know it's the a value. It's still going to be the a value, but then we have to compensate for that. So if we factor that, don't factor out the x's. We need the quadratic to stay in place. So it's just the linear or the numerical coefficient that's coming out. So this is now x squared plus 4x, and of course we're going to leave the 7 alone. Now that we've done that, the linear coefficient, the b value, is now 4. Well, for completing the square purposes, you guys know it's b over 2 quantity squared. So that's 4 over 2 squared. 2 squared is 4. So to create the PST, I need to add 4. And I'm going to do exactly that. However, once again, I can't add 4 to the other side. There isn't another side to add it to. So even though this doesn't seem to make good sense, do it anyway. As soon as I put that 4 in, I'm going to turn around and I'm going to take it back out on the same side. And of course this plus 7 is still there. Now I want to capture that PST that I've just worked so hard to create, and there it is. So I'm going to bump this guy out. This might be -4, the subtracting of the positive 4 that I just taken out, I'm bumping it out. But don't forget, and this is the toughest part, not only is it a -4, it was multiplied by 2. So when I regroup, when I reassociate, it's 2 times the -4 plus 7. Rewrite the PST then as the binomial squared. There it is. A is still A. Well, let's get friends together over here. This is really what? -8 plus 7. The net effect of that is -1. So now I have 2 times x plus 2 quantity squared as the standard form. And if I compare this standard form to the standard form over here, they are in fact identical. So I can use vertex method to transform from general form to standard form. I also can complete the square. The goal, again, is to be able to sketch by hand, to be able to transform or to use the transformations of the parent function f of x equals x squared, and to recognize and to appreciate that I've moved left 2. This plus 2 tells me that vertex has gone left 2 units. And this -1 tells me I've gone down 1 unit. And this 2 times, well, first of all, 2 is greater than 0, so we know that we open up. But we also have a V stretch, a vertical stretch, by a factor of 2. So now we've started to algebraically manipulate general form to standard form to analyze graphs. If you would with me, please move ahead in the text to the homework section on page 250. Your first assignment starts at problem number 5, which is a matching exercise so that you can view the transformed graphs and their associated equations. 9 through 16, we ask you to actually sketch by hand. See if you can't take the form, which is already set up in the standard form, that you can do the actual sketching. Numbers 17 through 30 then say to describe the function and identify its vertex. Then plug it into your graphing calculator to check your results. The discussion that we've had so far today should get you all the way to the end of this first assignment. Again, we're looking for vertex. We're looking to see whether the parabola is opening up or down. We're identifying x equals a number. Well, what number? The x value of the vertex. That's going to tell you where the line of symmetry is. Once we have that information, we should be able to sketch by hand, comparing the parent function with the transformation function. This ends the first lecture for 3.1. There's more to the story, but again, homework due today, the 23rd, by 9 p.m. this evening. Please digitally upload for me your work, which again is on page 250 of the textbook, numbers 5 through 30.